But when we're talking about oceans, especially ocean water, we care about what's dissolved inside of that water. Hopefully, we're all aware that ocean water is salty. It's saline. So where is all of that salinity or saltiness coming from? When we're looking at salt water, we want to know about the amount of solid materials that have been dissolved inside of it. Think back to our chapter on streams, where we had the dissolved load of sediment, where it's so small it dissolves inside of the water. With our salinity, we see that it's still dissolved solids inside of our water. But when it comes to salinity, the dissolved material makes up a very small percentage overall. So we could express it as a percent, but it would be something like 0.0035%, which doesn't sound very easy, especially if you're like me and you're not very math-minded. So instead of expressing it as a percent, a lot of the times we say parts per thousand. So instead of saying 0.00035%, we could just say it's 35 parts per thousand. For every 1,000 molecules, 35 of them are solid substances and the rest are water molecules. But when we look at all the different types of salts inside of our seawater, the most common one is sodium chloride, the same thing that makes up halite, the mineral, and our table salt. But when we actually look at all of the different types of salts that are dissolved inside of our water, sodium chloride is not the only one. Again, it's the most common and abundant salt, but it is not the only salt. We also have magnesium chloride, sodium sulfate, calcium chloride. Here, the idea is not that you need to know all of these different salts. I just want you to be aware that when we're talking about salt water, we have about a dozen different salts in differing amounts. But the most abundant salt is sodium chloride, our table salt. So where are all of these different salts coming from? We see that most of the salt that makes up our ocean waters actually coming from our continental rocks. Those felsic, granitic rocks that are being weathered over time. So over millions of years, those continents are being weathered and broken down until eventually they're so small that they dissolve inside of water. So most of the salt in our salt water comes from our continents, the rocks themselves. But a very small percent also comes from the mantle, the interior of our planet, from volcanic eruptions where magma is being brought to the surface as lava. But if we look at the composition of seawater, what kind of different salts and in what amount, we see that it's been relatively stable for millions of years. The saltiness of our oceans has not changed very much, even over long periods of time, because as we start removing salts from our salt water, we have the same amount being added by more continental weathering of those rocks. If we look at this chart here on the right, we'll see that temperature, which is shown in the red line, gets the highest around our equator, which should be fairly obvious. The warmest part of our planet is the equator because it gets the most sunlight, and then our poles, because they're so cold, have lower temperatures because they're not getting as much sunlight. But if we look at how salinity changes across our planet, which is shown here in blue, you'll notice it's not as obvious of how it changes. And that's because salinity changes when we're either adding or removing fresh water from the surface of our oceans. So if we're adding fresh water, and fresh water is just water that is not salty, fresh water is what we drink. If we start adding in fresh water to the surface, it's going to decrease the salinity overall. It's going to be diluting what dissolved solids we have by adding more fresh water to it. And some of the ways that we can add fresh water to our oceans, from precipitation. It always rains fresh water. But we also have a ton of runoff coming from our continents, where we have those rivers that are discharging into the ocean. And unfortunately, we also have a lot of icebergs and sea ice that are melting. That ice is melting and releasing fresh water into our oceans. So when we add fresh water, it decreases the salinity because we're diluting it. But if we start removing the fresh water, it's actually going to increase the salinity. And this is because we're doing the exact opposite of diluting it. Now, if we're removing the water molecules and leaving the salts behind, it's going to become more concentrated. It'll become saltier as we remove that fresh water. And a couple of the ways that we can remove fresh water is through evaporation, where the surface of our oceans receive sunlight, they heat up, and that water evaporates. And in some locations, we see that sea ice is actually forming. It's getting colder, and that liquid water is freezing as solid ice. And when ice freezes, it does not freeze whatever's dissolved inside of the water. It only freezes the fresh water, leaving the salts behind. But overall, we're going to see that the exact salinity of a location is going to change based on its seasons. And we're going to see that salinity will also change based on its latitude. This image is just showing us how salinity actually differs on our planet, where we see that our cooler colors, our purples and our blues, are lower salinity. They're freshwater, or closer to freshwater, whereas our oranges and reds are the highest salinity. They're very, very salty. So if we look at where the Amazon River is discharging into the Atlantic Ocean, we can see that it's dark blue. Here, adding fresh water from this river is going to decrease the salinity of our oceans. We see the same thing going on in the Bay of Bengal, where we have the Ganges River emptying, and it leads to really low salinity water. But on the opposite end of the spectrum, if we look at the Arabian Sea, you'll notice that it's bright yellow with orange. Here we have a much higher salinity because it's Arabia. We have high amounts of evaporation, leading that water to become saltier or higher salinity. You probably are already aware, but climate change is happening on our planet. Overall, our planet has warmed up about 1.5 degrees Celsius. Doesn't sound like a lot, but in our polar regions where it's really cold, warming the air a couple of degrees can cause the ice to melt very quickly. So in this image, we're seeing in this blue outline where the ice limit used to be, whereas shown here in red is where the ice limit is today. Our icebergs and our ice sheets are getting smaller and smaller because they're melting. But as they melt, all of the water that's stored in the ice is going to be released as a liquid. And remember from earlier that when ice freezes, it does not incorporate whatever's dissolved inside of the water. It only freezes the water. So if I try to freeze a tray or an ice tray full of salt water, I will have a perfectly pure salt cube at the top, and then at the bottom I'll have a layer of just salt. It's not incorporated into the ice. But here in this image, as our sea ice starts to diminish in its extent, it's melting, releasing tons of fresh water to the surface, where it will significantly decrease the salinity of the water. And that brings me to our next point. We, as humans, are having major impacts on our oceans. And that's because a lot of what we do revolves around burning fossil fuels and cutting down trees so that humans have places to live and grow food. But these human activities add greenhouse gases to our atmosphere. And we'll talk about this in a few more chapters. But greenhouse gases act like blankets. And I don't know about you all, but I like to sleep with one blanket. If I don't have a blanket when I try to sleep, I'm uncomfortable and I don't sleep well. But at the same time, if you put 20 blankets on my bed, I'm going to be so hot I can't sleep either. And greenhouse gases, to me, are kind of like blankets. We need some greenhouse gases to keep our planet warm enough so life can exist. But the issue is that with human activities, we're adding too many greenhouse gases to our atmosphere. Now, instead of my bed just having one blanket on it, now it does have 20. It leads to our planet warming up very quickly, just like I would get really hot trying to sleep underneath 20 blankets. But one of the issues when it comes to adding greenhouse gases to our atmosphere is that when that atmosphere, those gases come in contact with our seawater, it forms something called carbonic acid. When we have more carbonic acid in our seawater, it's literally just an acid. It's going to start eating things away. It's going to make it very difficult for marine life to continue, especially if it's shell-building animals, like corals and clams and oysters that build their shells out of calcite. Because remember, that mineral calcite reacts to acid. It bubbles and effervesces. So when we have a lot of carbonic acid in our seawater, that acidity literally eats the shells away. Life is going to find it very difficult to exist. And unfortunately, this is leading to the destruction of all the coral reefs on our planet. Right now, the Great Barrier Reef in Australia is over 50% dead, and this has happened in just the last few decades due to the rising acidity in our oceans, due to the fact that we're adding too much carbon dioxide into our air.